Hello, everyone. I hope you're all doing well. I'm all right and hope to be back there at school with you all shortly. Today on page 11, we're going to be talking about a couple of words that we've honestly been throwing around a lot, almost interchangeably. And that's accuracy and precision. And today, I really want to nail down the difference between them and when it's important to be accurate, precise. Well, of course, we hope we can be both, but a little bit more understanding what the difference is between them, because we're not always going to be both. So accurate or accuracy is sometimes what I think of as accurate. It's about how close the measured value or your attempt in the experiment is to the actual accepted value, how close you are to being right. Precision, on the other hand, is about how close a series of measurements or attempts are to one another. So how reproducible they are, whether or not you can do the same thing and get the same results over and over and over again. Notice how this precision has nothing to do about whether or not you're close to the right answer. It's just about whether your attempts, your measurements, your trials are close to one another. And that's one of the first differences between these words, is that you cannot be precise unless you make multiple attempts. And that's why in science, we always do multiple trials of the same thing or similar things in order to establish this precision and know that we're being precise with our measurements. And then if we do take more than one trial in the lab, we'll probably have to take the average of those trials, and then that's the value that we're going to compare to that true value. And the closer we are to that true value, then the more accurate we are. Which could be a good thing to write down, perhaps, because we're going to be determining people's accuracy and precision here in a moment. Precision in the lab, you're just going to look at the values that you have, whatever range they have, meaning subtract the biggest from the smallest, see how far apart they are. And, of course, the smaller that range, the closer that they are together, and the more precise those measurements are. So let's look at some simple examples. We're not always going to be able to look at darts in a dartboard, but it's a nice way to start to understand the difference between these words. So this first purple set of darts that were thrown at the dartboard, we have to figure out, are they accurate, precise, both, or neither? So remember, with accurate, it's really about accurate. Are they hitting the target? And no, they really aren't. None of them are really coming in even into that inner three circles. So I would say they're not accurate. Precise? No, they're also all over the place. So I would say they are neither. And that's really kind of the beginner level, where you don't know what you're doing. You're just tossing darts and making adjustments. You're probably not going to hit the target very often, and your shots are probably going to be not very close to each other. Target B with the pink darts, they are not accurate because, once again, they are nowhere near the target. In fact, most of them are farther away than the purple set of darts, but they are very closely grouped together. So these darts are precise, but not accurate. And this is often an indicator of an intermediate learner, is they're able to make repeated measurements predictably, even if there's something wrong with what they're doing still, where they're not making perfect measurements, perfect shots every time. They're at least doing the same thing over and over again, and then an expert can come in and perfect that one thing that they're doing wrong, and then they can get to that expert level, where hopefully, like the green darts here, they're all hitting the center, and they're all grouped together, so they are both accurate and precise. That's that master expert level skill being shown there. Now, like I said, we're not always going to be looking at darts, so we need to be able to look at numbers and make the same kind of decisions about accuracy and precision. And here I've gone ahead and found the average and the range for a set of data that you're given there in your packet. And it doesn't actually say the scenario, like what you would see in a traditional word problem. So if you wanted to jot this down someplace in that area by that table, just so that it makes more sense when you go back and look at this and look at this type of problem and study for this kind of thing showing up on your test, because it will, Just make sure you leave a little bit of space as you're writing down that scenario, if you do, to go through and decide who's most accurate, most precise, least precise, because that's what we're going to be doing in this space here. So, in the future, you are going to have to calculate your own averages and ranges, so down here might be the best place. Before we actually go into and make these decisions, let's make a quick note about how to calculate an average, because I'm not there if some of you have this question. Help each other out with the actual calculation process that you're going to be going through, but at the same time, hopefully if you need that help, you write this down in your notes. So for an average, all you have to do is add up each of the trial numbers for each student. So here I have 4 trials, so we add up trial 1, 2, 3, and 4 for each student. If you had more than 4 trials for a single measurement or student, then you'd add up all of those trials. And then you're going to divide by the number of trials that you had. So in here, that would have been 4. If you added up 5 trials worth of data, 5 measurements, then you divide by 5. A range is much simpler. A range, like I said previously actually, is just the biggest or largest value minus the smallest, just to see how far apart the farthest 2 measurements in any set are. So you have to have at least 2. If that's all you got, then just subtract those 2 numbers. If you got more, you have to pay a little more attention to each of the numbers. So if you're in any doubt as to your skills with these averages and ranges, try it out with this set of data. See if you get the same answers that I got. If you don't, then ask for help from someone around you or me when I return soon. So now let's get on with considering the results of these 3 students and figuring out who was the most accurate, most precise, and least precise. So if we're starting with accuracy, remember this is all about being right. So this is all about how close our students average. For that accuracy, we are going to look at the average and see which one of those values is closest to the right value. And hopefully you can see the closest one here, the most accurate student, is student C, because their average is closest to 10. The least accurate person then is the person whose average is farthest away from 10. And hopefully you agree that that is student B. Precision now is about how close these are together. Precision is about that range, and our smallest range is going to be the one that is most precise. So which of these 3 numbers is the smallest? And it only wins by a hair, but this one, our most precise, is going to be student C. So they are both the most accurate and the most precise. And now the least precise is going to be the one with the largest range. The biggest range is student A. So these are kind of the 4 things that we're looking for. If we're talking about precision and I ask you about student B's precision specifically, you can tell me that they're kind of in the middle. They're not the most or least precise, that kind of thing. It's still descriptive, but it's usually most helpful when you're comparing people to each other to know who's the most or least accurate and precise. So now, let's go ahead and get you guys trying this out on your own on page 12. Just questions 1 and 2 have to do with this accuracy, precision stuff, finding the average and range, and determining a little bit about accuracy and precision of those measurements. And then we'll finish out page 11, and you can finish out the rest of your page 12 practice. I did want to point out, though, for number 1, I have posted the averages and ranges on Canvas, but I want you to try and calculate them first, kind of like what I said with this last problem. You're going to have to do this on your own on tests and quizzes, so you need to figure out if you can find averages and ranges. So try them on your own first. Double check your numbers with mine and Canvas before you make any decisions on who's most accurate, least accurate, that kind of thing. Trust your numbers first and then make those decisions, and you can be more confident in those answers. Because I have not posted who was most accurate, least accurate. I haven't actually answered the question, but I've given you all of the numbers you need to make sure you're answering it correctly when you do that. Also, on that page, when you look at it, it is going to ask you for details about all of the people, Lisa, Seth, and Evan. And if you describe who's most accurate, least accurate, most precise, least precise, then everyone will have something special about them to say. No one is going to be in the middle for both of them. And FYI, there will be a tie for one of them. So that's all that I really need there when it says to describe the accuracy and precision of each student's mass measurements. Just tell me who's most and least of each of these important things, and you're good. And if you'd prefer to just go ahead and continue watching and filling in page 11 notes so that you can just do all of your page 12 practice all at once, I don't blame you. It's up to you how you do your notes and practice. Let's just get both of those pages done in class today. So, finishing out page 11 here, pause if you want to finish 12 real quick. We're going to talk about this thing called percent error. And percent error is a measure of accuracy. It helps us compare numbers and compare different measurements' accuracy to know better kind of how accurate is good accurate. Because in some of these other examples, I mean, you just have to choose whoever's closest to right. But what if that's not close enough to really count as accurate? With a target, we always know kind of what everyone's trying to hit. But with scientific measurements, everyone's measuring different values, and sometimes it's hard to know how close is close enough. And a good example of that is if I tell you, well, just for context, I'm 5 off of my measurement, or whatever I was counting, say jelly beans. And you're like, okay, 5's not that bad. Well, but what if I tell you I was only counting 6 jelly beans and I'm 5 off? How, suddenly you doubt whether or not I should be your chemistry teacher. But if I was 5 off of 1,000,000 jelly beans, then that's pretty good. That's amazing, actually. So being 5 off tells me how far away I am from that correct true value, but it has no context for the size of that measurement or of that value, and as such, it can be completely worthless, and it still leaves people guessing as to, is that good? Is 5 off good? Tell me more. So percent error accounts for this, and the way it does that, hopefully you've possibly already written this down as I've been talking about the context of this, but our definition of percent error is the difference between the experimental value and the accepted value. That's what these E's and A's are here. And those are going to be the 2 most important things for you to find in any kind of percent error problem and tell the difference between. The experimental value is the thing that someone tried to measure in an experiment. It's not always perfect, but that's what someone tried their best on. The accepted value, the A value, is the true value. That's what people know or accept to be correct. So the first part of the percent error calculation itself, which you should write down this equation, is finding the difference between these two, subtracting them. So seeing how far away the range between these two values. But then it does something important. It divides by the accepted value. So if I divide by a small number, then that gives me a really big percent error. But the bigger number that I'm dividing by, the bigger my accepted value, the bigger my measurement is supposed to be, then the smaller my percent error becomes. So with the same difference between my value, my attempt, my experiment, and the truth, the larger and larger the measurement, then the more acceptable that error is. Like we kind of said, 5 off out of 1,000,000, no big deal, not at all. So, and then of course, because it's a percent, we're multiplying by 100. So, all we really got to do in these problems is figure out what our E and our A is, plug it in, and do the calculation. Everything else just kind of falls into place. So, let's try one of these problems. Quick note in the calculator, if you like to plug everything in all at once, you're going to need to remember to use these parentheses that we've got here in the equation, because otherwise you're going to end up dividing. It's an order of operations, PEMDAS things, but If you'd like to do this in the calculators and you really don't like parentheses, then do the subtraction first, push enter, and then do your divided by a and times 100, and then push enter again. If you do that subtraction first, it's kind of its own separate step, and push enter in between, it will all work out fine. Otherwise, you gotta use parentheses. So, let's try some of these problems out. So, first problem says there's 34 questions on a test. John only answers 22 of them correctly. What is his percent error? So you might be going, what? This doesn't seem like a science measurement question. But this is still a student making an attempt at something. And if we ask ourselves, out of these two numbers in the problem, which one was John's experimental attempt, his best effort, but that might not have been perfect? Well, that's the 22. John only answered 22 of the questions on the test correctly. That was his experimental attempt at answering questions on this test. What is the accepted value, the correct number of questions he could have gotten in a perfect world? Well, that's 34. That's the accepted value, the accepted number of questions, the maximum he could have gotten correct. So with that decided, now we just need to plug into that equation and do our E minus A. So that is 22 minus 34. Divide by our A and multiply by 100. Like I said, if you do that top part first, then this can sometimes work out better. So 22 minus 34, and yes, that sign is correct, is negative 12. Now, hold on, I'll explain the negative in a second. We still have to do all the rest of that math. So dividing by 34 and times 100 can all happen at once, and everything will still happen correctly. You can also do that in two separate steps, but up to you. And what my calculator is telling me, all the numbers that are coming out, is negative 35.29411. And you might be asking, Mrs. Gunter, but do we need to write all of those numbers? And of course we don't. We're going to round that answer. But I just wanted to make sure that you were pushing the same buttons that I was. We're getting the same answers out in our calculator. If you're not, double check that. Now, first off, two things. This negative sign. The negative sign on this percent error tells us that we are lower than what we were aiming for. Our error is that we are too small, which on a test makes sense. You wouldn't make an error by going above and beyond and answering more questions than what you got. But there are situations in chemistry where you could have too much stuff left over, which would actually be an error. So we can have positive error, but most normal issues in our world, in kind of normal non-science world, I guess, will be negative error. So don't be afraid of the negative. It's just there. Now, rounding. Look at the sig figs that we started with. All of these numbers had two significant figures. So we want our answer to have two significant figures. So our final answer here is going to be negative 35%, because those are the first two sig figs in the number, and that 2 did not round my 5 up. So that's our final answer here. In this next problem, it says that our rope is 2.15 feet long. John measured the rope as 1.85 feet. As we've seen by his test results, he has a tendency to have some error. So he made an attempt. He tried his best at measuring this rope, and maybe it was mispackaged, but maybe he just mismeasured it somehow, made a mistake, and his experimental attempt is at 1.85. The accepted value, the labeled value on there that most people would accept as the true length, is 2.15 feet. So that's our A. So I want you to go ahead and finish out working this problem. I will go ahead and tell you this answer is going to be negative, and I will go ahead and point out that both of these numbers have 3 significant figures. So make sure your answer has 3 significant figures in it as well, and the percent sign, of course, just to make sure it's labeled correctly. Feel free to talk and compare answers with the people around you in class just to make sure you're on the right track. But after that point, you should be ready to finish out all the rest of your page 12 practice. You do not have to do number 6. That one actually has you work backwards through a percent error problem, and you can do it if you got the math skills, but especially since I'm not there to help you with that kind of thing, you do not have to do that on page 12. Just number 6, feel free to skip it. I'm never going to ask you to do it in your packet. It won't count against you. And just FYI, all of the numerical answers to these calculation problems on page 12 have been posted on Canvas, but they will earn you no credit if you do not show the work. I need to see, at the very least, this level of plugging in the numbers from the problem, even if it's just this. Even if you just plug in the numbers and then you show me an answer, that's fine. That shows me what you think of as your E and your A, that you know where to put them there. So at the very least, I need the substituted equation and the final answer. So down here, just an answer will not cut it. I need to see substituted equation and that answer. And the same thing goes for that page 12 work as well. So that's our notes for today. Go ahead and work on page 12, and you might even have time to watch your page 13 podcast homework in class, because I don't want you to have homework. I'm sorry that it has to be so many videos while I'm out, but I'll be back real soon, I promise.